Good morning, friends. Hope you are all taking care of yourself. Welcome back to Dr. Sucheta's interactive class. Today, we are going to learn about one of the technique, flame emission spectroscopy. By looking at this first slide, looking at the colors of the flame, question might come in your mind how the color of the flame changes. So we are going to learn in detail about flame emission spectroscopy, its principle, working, components, applications, advantages and disadvantages. First of all, we'll try to see how the nature of the flame is there, which are the different zones of the flame are there, which are responsible to carry out the process of combustion. Now, this is an yellow flame. You might have used this burner, Mecker burner in lab, where if you close the air regulator, the flame color has been changed to yellow. Where oxygen supply you have removed, and hence the color of the flame changes. Now, looking at the regular flame over here, if I want to see the detail of this lower part is the part where unburned gas and air, slightly yellowish. If you observe in detail, actually it's slightly yellowish, where some unburned part is there which has comparatively low heat. This is the middle part of the zone, which is the hottest part, and here the upper part of the zone or outermost part where oxygen supply is sufficient, ample of oxygen supply, where complete combustion of the substance carried out, and the very hot temperature is there. Temperature is very high in this particular part. If I take any metal salt, inorganic metal salt we are dealing over here, if I take any metal salt, make a paste of it by putting a little amount of acid and organic solvent. If I take in contact with the flame, let us see which are the different processes happens. Yes, can you guess or tell me what will happen? Correct, it will vaporize, solvent will vaporize, and excellent. So we'll see in detail what will happen. Solvent get vaporized, leaving particles of the salt behind. Then the salt subsequently vaporize and dissociate it into atoms. Some of the atoms absorb thermal energy from the flame and they will get excited to higher energy level. Every atom, every element, when electron excite to higher energy level, it is unstable state. It releases its extra energy in the form of light or different colors. That is the process takes place. So this is the flame photometer instrument which will give me details about how we'll carry out this flame emission spectroscopy technique. There are major components where first is the sample delivery and metallic salt solution, which we have to spray through this nebulizer in contact with the flame along with the gas, fuel gas and oxidant. Once it starts burning, it emits energy. That emitted energy is channelized through this filter and lens and detected by a photodetector to amplify or readout device. So these are the basic components. We'll see in detail all these components in my future slides. This is the instrument which we are going to see in detail. The view of this instrument in lab, you can see this type of instrument. It looks like outer part. Here the digital device will give you the reading in terms of absorbance. So the basic principle of flame photometry we can write in form as when a salt solution is spread as a fine droplets into flame. Due to the heat of the flame, the droplets get evaporated, leaving behind residue of the salt. This fine residue converts into neutral atoms. Due to the thermal energy of the flame, these atoms get excited and they return to the ground state. During this, they emit radiation of specific wavelength. This wavelength of radiation emitted is specific for every element. This point is very important. Wavelength of radiation emitted is specific for every element, where this particular point we are going to utilize to determine different element. So what actually the process takes place at atomic level? We'll see in detail. When metal comes in contact with the flame, it absorbs energy. It absorbs energy, and absorbed energy is utilized to lose an electron from the atom, which is termed as photoelectron, which absorbs energy and move to higher energy level. When it moves to higher energy level, when it comes back to lower energy level, it emits extra energy in the form of characteristic flame coloration. In fact, color arises due to these electronic transition of short-lived species. This process continues depending upon amount of salt is present in your sample solution, which is spread in contact with the flame. So the major components of flame photometric units is nebulizer, which carries out the fine droplets. Second is flame. Third is burner. Fourth one is mirror, slits, detector and readout device. Nebulizer. This is the component of sample delivery system which breaks up bigger liquid droplets into smaller liquid droplets. The process of conversion of sample to fine mist of finely divided droplets by using a jet of compressed gas is called nebulization. So what we are going to do over here, we are converting bigger liquid droplets into smaller liquid droplets. There are different types of nebulizers available in the market. We'll see their working. Pneumatic nebulizers, they are being called as, first is concentric tubes, second cross flow, Baggington, Fritted disc. Concentric tubes, where liquid sample is sucked through the capillary tube and it is coming at the nozzle, where from here the gas at high pressure, inert gas at high pressure, jet of this gas is flowing around the capillary, around the nozzle. High velocity of this particular gas breaks down your sample into mist, smaller droplets units. This is cross flow nebulizer. Name itself tells me that sample and the gas at high pressure both are moving in cross direction, perpendicular to each other. Sample is moving from this direction and your gas, argon gas at high pressure is coming from here, convert your fine drop into fine droplets which comes in contact further in the flame. This is Babbington nebulizer, where you are having a jet of argon compressed gas in the form of orifice in a sphere on which thin film of your sample is coming or flowing. This type of nebulizer, where sample solution flows freely over an aperture rather than passing through the capillary, and then it converts into aerosols. This is the last, Fritted or porous disc nebulizer, where sample is pumped into Fritted disc through which the gas jet is flowing. From here you can see in the diagram the gas, argon gas is flowing through this. This is the Fritted disc over which sample is flowing, and here I can introduce and convert this Fritted disc sample into fine droplets. Second component of your flame emission spectroscopic technique is burner. There are different types of burner available. Mecker burner, that is the regular lab burner which we are using. Total consumption burner, premix of laminar flow burner, Lindergraf burner, shielded burner, nitrous oxide, acetylene flames. Now, among these, which burner is suitable for my process? So, what characteristic of flame is expected from this burner? Yes, can you guess which type of flame you want to have during your experiment? Yes, one by one? Correct. It should give me a proper temperature and that should remain constant during the operation. And second one is Very good. There should be no fluctuation during the burning process. So these basic characteristic flame should have. We can obtain the flame with various temperature depending upon the utilization of fuel and oxidant. This table provides me a temperature range for different types of fuel. Oxyacetylene flame gives me higher temperature, routinely used for flame emission spectroscopy technique. This is the Mecker Burner, regular lab burner, which we are utilizing by use of natural gas and oxygen, produces relatively low temperature and low excitation energy. Total consumption burner, it is utilized in most of the instruments where, if I see the diagram, sample solution is having centrally flowed through the capillary. You are having fuel and oxidant which are moving through the separate pipe, and all of them are reaching at the top at the same time, where sample solution is aspirated. Here utilization of entire sample happens. Entire sample is consumed when it comes in contact with the burner. Premix or laminar flow burner. The name premix itself tells me that sample and fuel and oxidants are mixed before they reach to the burner. So here the process takes place in this chamber where sample is aspirated, oxidant is entered, fuel is entered, all of them are mixing. This process happens like they are converted into small gaseous mist sample. Due to pressure they are moving fast. They may bombard on this mining baffles, again reach back, and with high pressure they goes at the burner. When this process takes place, only few amount of the sample reach at the flame. 95% of the sample get drained out. Lindgraf burners. In this, sample and air are mixed in a chamber. This mixed composition is allowed to apply through the burner head. Here also utilization of sample is very less. Now we move to the next part of the component, that is mirror. Once the process of burning of your sample takes place in this flame, evaporation, burning, absorption of energy takes place, the release of energy is observed in the form of different colors of the flame. This imparts in all directions. So we need to channelize this emitted energy for better detection. So mirror has been placed behind the burner which channelize this reflected radiations towards the slit and filter or monochromator further. Slits. Entrance and exit slits are utilized before and after dispersion of the element. Here, most of the radiations move surrounding. Entrance slit cuts most of the radiation from the surrounding, and it allows only the radiations from the flame and the mirror to enter into optical system, and it will be placed after monochromator. This monochromator channelize again the radiations and it detects. Entrance and exit slits are placed before and after the dispersion of the elements. Entrance slit cuts off most of the radiation from the surrounding and allows only the radiation from the flame and the mirror of reflection flame enter into optical system. Exit slit is placed after the monochromator, which allows only selected wavelength of radiation to pass through the detector unit. There are different detectors we are utilizing over here. Like we want to convert the emitted energy, that is light energy, into electrical energy, photon energy into electrical energy. So we want to have a detector which detects photon and converts its energy into electrical energy. So do you know which are the different types of detectors? Yes, photocell, phototube and photomultiplier cell. We'll have a quick review how they works over here. Photocell, it is actually an PN junction. and semiconductor, which we are utilizing along with galvanometer. When emitted energy in the form of light, photons come and strike in this upper part. Transparent metal has been utilized over here. When it strikes, it converts photons into electrons. There is release of electrons at this place, and through this p-n junction, it is absorbed at the highly conductive metal like silver over here. This electrical potential difference has been generated through this particular p-n junction, and which is measured by galvanometer. The second type of detector is phototube, and glass evacuated tube has been utilized over here. This is the cathode where all the photons strikes over the cathode. It releases the electron absorbed by the anode, and the light energy has been detected. Amount of the light energy, we can correlate this absorbance with concentration of the salt present in your sample solution. We can amplify the result over here. If we want to amplify the result to higher level for very low concentration, as in flame photometry, we are using very low concentration like ppm and ppm, parts per million, 1 milligram per liter. So this is the third type of detector which amplifies the result. We'll see how it is. Photomultiplier unit. Number of photons which are coming over the detector, which strikes as this diodes. These are the cathodes which are arranged alternate to each other with high voltage. How it works? One electron strikes, it emits 2 to 4, 4 to 8, 8 to 16, like that. The signal has been multiplied and detected. When we are carrying out this particular process, there are little interferences during the analysis. Some are chemical interferences, some are spectral interferences, and some might happen due to background radiation. Now we'll see what is chemical interference, which happens when you are spraying a salt solution in contact with the flame. Sometimes atom may react with the flame reacts with the atom. It may produce some other species. Also, emission has been decreased over here due to this process of reaction. Spectral interferences happens when you are having mixture of, suppose the sample mixture of salt solution or like water sample you are spraying in contact. If it has an elements which are having their emission energy little bit of same wavelength, then the signal will get overlapped, and that's why the spectral interference observed when emission of such species takes place in contact with the flame. Background radiations, the signal obtained here when you are carrying out flame emission spectroscopic technique. What happens? Your atom absorbs energy, goes into higher energy level and comes back to lower energy level. This causes and line spectra. The process continues. Process continues. These line spectra observed by flame excitation are superimposed upon continuous background radiation which are arise in a part of flame itself. Continuous spectra of various compounds are also responsible for background radiations. We can apply this technique, we can carry out in lab qualitative and quantitative analysis. Now look at this photograph. It's self-explanatory. There are different metals written down, and every metal imparts different color. Now I can correlate this particular information when I carry out the analysis in lab to detect elements present in my given compound. We can quantitatively also carry out the analysis where we can find out the concentration of sample. We can carry out the quantitative analysis by 3 different methods. First is calibration curve method. In calibration curve method, we want to have an element which we want to detect. For example, we want to detect the concentration of potassium. Now, we should have to have a salt where known concentration of solutions are prepared as a set of solutions will prepare with known concentration as milligram per liter or ppm solution. So different ppm solutions are there with me, and an unknown solution has been provided to you for which you want to determine the concentration. So we'll carry out the process of flame emission spectroscopic technique to obtain the data of absorbance of known concentration solution. We'll plot them as a calibration curve where we apply Lambert's Beer's law specifically, where absorbance is directly proportional to concentration and straight line passing through origin. Now, an unknown solution which has been provided to you, will run that solution through flame emission spectroscopy and we'll find out absorbance for unknown solution. And once we know the absorbance for unknown solution, suppose this is 0.03, we'll have a line we can drag from 0.03 over this calibration curve will come down, and we can note the concentration as 1 point some value, 1.3 suppose milligram per liter. So this is calibration curve method. The second method we can apply for quantitative analysis is standard addition method. Suppose we are carrying out or applying calibration curve method and we are unable to find out the concentration of sample which has been provided to us. So we can find out the concentration by adding standard solution of the same element. Suppose strontium, standard solution, known concentration solution will prepare as a stock solution and will add known amount of it in all different solutions, a set of solutions of unknown sample which has been provided to you. We'll carry out the analysis and we'll have a graph where absorbance versus concentration and which intersect at this y-axis. We intersect at this axis and we can find out the concentration as 1.74 ppm. Quantitative analysis by internal standard method. Now we'll look into detail for this internal standard process, how we can carry out. Known amount of internal standard element has been added into sample as well as standard. We are adding a known internal standard into sample to magnify the signal as well as standard, and the ratio of intensity of these sample as well as standard, ratio of them is plotted against the concentration to prepare a calibration curve. Intensity of each line is corrected for its background radiation, like in colorimetry or in any other analysis. We'll put a blank, we'll find out their reading, and if it is not possible to make auto zero, we'll remove or we'll minus that reading. Same process, intensity of each line is corrected for background correction and straight line is obtained when log of emission ratio versus log of concentration of element. So we'll look for advantages of FES. It is very quick, convenient, selective and sensitive analysis. It is both qualitative and quantitative analysis we can carry out. We can carry out for very low concentration ppm and ppb level concentration for metal determination. The method of analysis is very simple, economical. This method compensates for any unexpected interfering material present in sample solution, and it can be used for estimation of elements which are rarely analyzed. If we look at the disadvantages, can you tell me any one disadvantage of this process? Yes, we can't do 2 or more elements at a time. Very good. Accurate determination of metal cannot be measured. It cannot be directly applied for presence of inert gases. Even though it measures the metal concentration, it can't provide any information of molecular structure of the metal present in a sample. Only liquid samples we can apply. We have to prepare a sample, which is little bit a long process to prepare a ppm solution and liquid sample solution which are spraying in contact with the phlegm. This cannot be directly applied for determination of each and every element. We are having restriction for alkali, or it is commonly used for alkali and alkaline metals due to low ionization energy to release an electron during detection. Elements like carbon, hydrogen, halides cannot be detected. You can see for further details, you can go through these references. Chetwal Anand, Instrumental Methods of Analysis. This is very good book. And B.K. Sharma, Instrumental Methods of Chemical Analysis. Thank you. Hope you have understood the depth of knowledge through this video of FES flame emission spectroscopy. If you like this video, please press the button like, share and subscribe this video. I'm waiting for your suggestions, and my next video will be there on atomic absorption spectroscopy. Thank you.